Consider the function f that is continuous on the interval -5, 5, and for which the integral from 0 to 5 is equal to 4. Evaluate each integral a, b, c, d. So we know that a certain function, I'll just randomly draw it like that, is such that the area under the curve, between the curve and the x-axis from x equals 0 to x equals 5, is 4. By the way, I'm showing a function that is above the x-axis everywhere, but it's also possible that f of x is something like that, and that this area minus this area plus this area equals to 4. But it's going to be probably easier to just focus on a function like this one here. So what can we say in question A about the function f of x plus 2? If you remember from previous classes, this plus 2 has the effect that it is a vertical translation 2 units up. So now we are maybe up here. So this is f of x plus 2. So there's two ways of thinking about how to figure out the area under the graph. Now, the first way is to remember what f of x was and think, well, I know that this is 4, and now how much is this extra area here, because everything moved up by 2. And even though this is perfectly sound logically, this area here is exactly what we're looking for and what we need to add to 4. It's actually not very practical. It's not so easy to find out what this area is. So, another way of interpreting the exact same function f of x plus 2 is like this. It's to say, well, the function went up, and I'm going to take the entire area 4, so it has the same shape as this here. This is equal to 4. And what's added to that is below it. Instead of thinking we've added above, we can think that we've added below. And that's a rectangle, so it's a lot easier to find out the area. The area is base times height, so it's 5 times 2, and therefore there's an area of 10 here. So final answer, 4 plus 10. That also brings us to an interesting fact that even though this is not a rectangle, it has the same area as the rectangle if you just measure like this, 5 times the height, 2. Also, another way of solving this exercise was not thinking in terms of geometry, but in terms of algebra. The integral from 0 to 5 of f of x plus 2 dx can be written as the integral from 0 to 5 of f of x dx plus the integral from 0 to 5 of 2 dx. Now this is equal to 4, we know it, and this here is a horizontal line at y equals 2 that we are integrating from 0 to 5, so we can easily find that it's equal to 10. You can also say the integral is 2x, so it's 2 times 5 minus 2 times 0. And that also yields a total of 14. By the way, doing it this way really exhibits the rectangle we had here. This rectangle with an area of 10 is the same as the area under the graph of y equals 2 here. What about question B? In question B, we have the function f of x plus 2. And moreover, we are integrating now from -2 to 3. This is another transformation that we study in Algebra 2 and Pre-Calculus, and it is called a horizontal shift 2 units to the left. If you have x equals 3, well, you're actually finding the value at f of 5. So everything is moved 2 to the left because it reaches 2 to the right to find the answer. So the graph of f is going to now look something like that. It's been moved 2 units to the left, and miraculously, sorry, there's a minus here, miraculously for this exercise, the bounds of the integrals have also moved by 2. So what this means is that the area here is exactly the same as that one here. It's just been shifted, and therefore the answer is 4. We can introduce a concept that we will study further later in the chapter, which is U substitution, to also solve this exercise in a different way. What you can do is you can set up U as x plus 2. So U equals x plus 2. And from there, you can find what this integral is in terms of U. Firstly, we need to change the bounds. When x equals negative 2, U is negative 2 plus 2, which is 0. When x is 3, U is 3 plus 2 equals 5. So I'm rewriting an integral where everything is in terms of U. The bounds are in terms of U. The variable is in terms of U, so it's f of U. And also, it can't be dx, it has to be du. So we need to find out what du is. If we take the derivative here, du dx equals 1. So if I multiply by dx, I get du equals dx. So I don't have anything to change. I can just say that this is du because it's equal to dx. And now, when we just focus on that, it's exactly what we have up there. We just changed all the letters, but the meaning and the area defined is exactly the same, so this would be equal to 4. Questions C and D use properties of functions. In question C, we have a function f that is even, which means it's symmetrical about the y-axis. So if my function f is like that, then now I know what's happening to my function f on the other side, because it's symmetrical. F even means f of x equals f of negative x. F of 5 is equal to f of negative 5. F of 1 is equal to f of negative 1. So now the question asks, what is the integral from negative 5 to 5 of f of x dx? So what's the area under the graph here? Well, there's 4 on this side and there's 4 on the other side, so the answer is 8. That kind of thinking can help us in question D. I'm going to stick to the same function that I've used from the beginning, even though it's not the most natural odd function we can think of. But if f is like this, an odd function is a function such that f of negative x equals negative f of x. So everything is symmetrical about the origin. So if f is odd, that means the function is actually something like that. So what is the area between, what is the signed area? Now it's pretty important to say that. What is the signed area between function f and the x-axis? We have all of this, which is going to yield a negative number, and then we have all of that, which yields 4. Clearly, this is negative 4 since it's symmetrical. So the answer to question D is 0. It's quite rare to see an odd function that would have a jump like that. Oftentimes, an odd function would be more like that. It would go through the origin. An exception to going through the origin is y equals 1 over x. This is also an odd function. You can see that it's symmetrical. Oh, I'm so sorry. This is an odd function that goes through the origin. This is a function that doesn't go through the origin, y equals 1 over x. But these are two odd functions that we see more often than this strange thing. But in any case, if this area is 4, then this integral is -4, and they cancel out. Because the exercise specifies that f is continuous, this would not be an example of a function we could have in this exercise. Okay, there's another exercise that I want to go over with. It's question 75. The reason is it's in fact not a very difficult exercise, but there's lots of numbers and we probably struggle to understand what is asked here. So find the Riemann sum for f of x equals x squared plus 3x over the interval 0, 8. x0 equals 0, x1 equals 1, x2 equals 3, x3 equals 7, x4 equals 8, c1 equals 1, c2 equals 2, c3 equals 5, c4 equals 8. What is that? Well, it gives us actually information about the rectangles that we're going to use for this Riemann sum. We're looking for the area in pink here, and the x0, 1, 2, 3, 4 gives us the base of the rectangles. We're going from x0 to x1, so we're going from 0 to 1, then we're going to go from 1 to 3, then we're going to go from 3 to 7, and finally we're going from 7 to 8. So this explains these numbers 0, 1, 3, 7, and 8. And now, how do we decide how high the rectangles are? Are we using RRAM? Are we using LRAM? MRAM? We're going to use actually points that are defined here. So for the first rectangle, we use x equals 1 to determine how high the rectangle is. For the second one, we use x equals 2. So the second rectangle goes from 1 to 3, but we pick x equals 2 to decide how high the rectangle is. In the third one, that goes from 3 to 7, we pick x equals 5. So something approximately like this. And finally, for the fourth rectangle, which goes from 7 to 8, we choose the value x equals 8 to determine the height of the rectangle. So here, there we go. So most of the time, what we do in calculus is choose LRAM, MRAM, or RRAM, but you in fact can use any of these, any combination. You could even choose here the value at 4 to decide how high the rectangle is. The fact is, whatever you choose, if you take infinitely many rectangles such that the base of all rectangles approaches 0, so if you do the limiting process, it doesn't matter anymore where you pick the point to determine the height. So you're allowed in Riemann sums to pick the point to determine the height anywhere, all the way from LRAM to RRAM, or any place in between inside the rectangle. So here, what's the area? For this one, we have a base of 1, which we need to multiply by the height. So the height of this rectangle is 1 squared plus 3 times 1, so it's 4. For the second rectangle here, we have a base of 2, and the height of the rectangle is determined by f of 2. So if I plug in 2 here, I get 4 plus 6, which is 10. The big rectangle here has a base of 4 and a height which is determined by x equals 5. So 25 plus 15 equals 40. And finally, the last rectangle has a base of 1 and its height is determined by x equals 8. So 64 plus 24, which is 88. So when you add all of this together, you find 272. So here's the final answer. Thank you.